Hi everyone. So I think we'll start our lecture again. But for those, first I need to thank people who remind me I should record the video because I realized I did not record our last lecture. But anyway, I'll put the lecture note, and I think it is not too complicated, so people should be able to follow the lecture note or read the textbook. Okay. So that's first thing. And the second thing is that I just heard from you that on the midterm exam week, there are electrodynamics midterm and the quantum mechanics midterm at the same time. So how many of you have taken the quantum mechanics? Please raise your hand so I know. Okay, so maybe more than 1/3, I guess, because some people is not here. How about the electromagnetism? How many of you have taken electromagnetism? Okay, so it's about 1/3. So thanks. So in that case, I think I'll send a official email to everybody to shift the midterm, such that you don't need to, take 3 midterms on the same week. Okay, so yeah, I think that would increase the chance of survival. So anyway, so that's a quick update. And I think we should be able to get back to our lecture. So now our goal is to identify what is T, and with the thermodynamic temperature that we are familiar with, basically the absolute temperature. Okay, so let's try to write down what is the definition of this thermodynamic the absolute temperature theta. So the way we define it is through the idea of the heat engine. Basically, from the elementary thermodynamics, we know the maximum efficiency of a thermal engine between two heat baths, basically theta 1 and theta 2, and we assume that theta 1 is larger than theta 2, and the efficiency of that heat engine is defined as eta equal to 1 minus theta 2 divided by theta 1. Okay, so that's like a way to define the absolute temperature from our understanding of the maximum efficiency basic heat engine, basically the Carnot cycle. Okay, so that's our goal. So let's consider our system starting from the heat engine. So let me try to draw that. Okay. So first we define the heat bath. So basically we have two heat baths. One is with T1 and the other is with some kind of temperature T2. And we know that this heat bath is a big object. So even though it can exchange energy with our system, but the temperature T1 and T2 are basically fixed. So let me just try to write down E1 and E2 as our initial energy configuration for our heat bath. Okay. And here we have some kind of piston. I don't know. And it is able to lift weights. And this piston can exchange energy with our heat bath. So it can, expand or compress in this thermal cycle. And also we assume that basically to the environment, there's no energy exchange. The only way that this engine can interact with the environment is through this work done by this piston. Okay, so that's the simple setting that we start with. So let me just try to write down what do I mean by that. So first we define what is a heat bath. So heat bath is something that has a fixed T. For system 1, it has T1, and for system 2, it has T2. Okay, and this T1 and T2 is independent of the energy E. And here, this description is about the heat bath. Okay, so that's one definition. And the second is the system. And we consider some kind of thermodynamic cycle. So for example, maybe we can write down the PV of this piston. And initially, it starts from some initial configuration. And it can do whatever it wants. I don't know, but eventually it went back to its initial configuration. That's what we define as a cycle for this thermodynamic process. Okay. So basically, after this cycle, what we found is that our system might have some change. So initially, we start from T1, E1, and T2, E2. But after this cycle, as we mentioned, since the energy can be exchanged between this piston and the heat bath, so the energy will also be changed from E1 to E1 prime. And the energy for the system 2, heat bath 2 will change from E2 to E2 prime. But as a definition of the heat bath, the T1 and T2, basically the temperature is not changed. Okay, so that's the settings that we have. Okay, so let me write down the second law of thermodynamics, which is the conserving of energy. Okay, so as we mentioned, because our system has no exchange of energy or heat with our environment, so the only way that it can exchange things is through the work that is done. Okay, so the change of energy is basically minus delta W, or we can say this delta W is minus dE. Okay, and from this process, like after this thermal cycle, we can simply ask what is the change of energy, because now the piston gets back to what it is originally. So the only difference is the energy of the heat bath. Okay, so the change of energy will be basically minus E1 prime plus E2 prime, subtract the E1 plus E2. Okay, and basically that will give us the energy difference. Okay, so that's the work done after this cycle. So by definition, we also need another quantity to define the efficiency of this heat engine. That's basically the heat that's put into the system, or put into the piston. Basically, eta is basically the work that's done. That's basically this quantity. Okay, divided by the heat or the energy that is transferred to this piston. So we want to ask what kind of function it will be. It's supposed to be some kind of function of T2 and T1, because the goal is that we want to connect this with the expression that we know from the conventional thermodynamics. So the expression for that is basically this. Okay, so that's our goal. But right now we just express the efficiency of this heat engine using this internal energy E. So the next question is how to convert that into the empirical temperature, or this T that we defined previously. So so now let's try to write down another expression that basically is something that we know. That is the entropy for our system at the initial stage should be like that. Okay. So after this cycle of the heat engine, we know that this entropy must be increasing. At least, you know, it cannot be smaller. It cannot reduce. So the initial amount of entropy should be smaller than the final amount of the entropy. Okay, so that's the condition that we know. And also, from the definition of our heat bath, we know that the temperature is related to this expression, or you can say 1 over T is just partial E partial S. Okay, so from here you can immediately reconstruct the expression of entropy for your individual system as a function of energy E and the temperature T. So I'll just write down the expression. Basically, the entropy for I system, I now runs from 1 or 2. Okay. So this is just the assumption that heat bath is not changing its temperature during this thermodynamic cycle. Okay. So so that's good, because if we have this expression and we know this inequality, we should be able to say something about the temperature. Basically, try to convert that into the relation of the of these energies. Okay, so let's see how it works. So now we try to insert this relation to this inequality. Okay, it should not be too complicated. What we will find is that the left-hand side, we basically did not touch it. Just keep it the way it is. And at the right-hand side, we use this expression. So we will have, okay, so we'll have this expression. And we'll see that this entropy value basically cancels each other. So we got an inequality only related to the energy and temperature. And that basically looks like. So now, if we have this relation, we can ask how to express this work done by our system, because now the work done by our system is basically and use this inequality. It must be smaller than okay. So it is not too complicated to do that. You can simply just put that in. Then this expression is good, because now we can evaluate what's the efficiency of this thermal engine, because what we need to do is divide by E1 minus E1 prime. So what we got is the efficiency can be described by this formal temperature T according to this relation. So now we can make a comparison with our, definition of efficiency using the absolute temperature. You'll see that, oh, actually we just proved that this T should be proportional with the absolute temperature theta. Okay. So in that sense, if we are able to define or fix this, the proportionality constant, for example, E equal to C theta, once we are able to fix this C, then everything is correctly described. So we basically follow the same logic about how we define absolute temperature. We take a physical phenomena, basically the triple point of water, and we define it to be 273 Kelvin. And then this proportionality constant C will be fixed. Then this formal temperature now is no longer a mathematical object. Now it becomes really the absolute temperature that we are familiar with. Okay. So that's something that I want to say. So why is the logic of like making this connection of this formal temperature and the formal and the absolute temperature is because remember that in this in the last course I only talk about the very at the very beginning about how to define temperature according to these assumptions of entropy, but I didn't really talk about what is the formal definition of pressure and the chemical potential. But once you go through that, you'll find that this formal definition of pressure and chemical potential actually is somehow related to whether you are able to make a real connection with the absolute temperature. So once you are able to make the absolute temperature, then make the connection with the absolute temperature, this T is physically meaningful. Then the formal definition of the pressure will also automatically be connected to the physical pressure that we are familiar with, and chemical potential similarly. So then the whole framework of thermodynamics can be defined using these postulates of entropy bit by bit. Okay, so that's basically the logic behind it. Okay, so are there any questions so far? Okay, so if not, let me try to continue. So now I'm going to talk about the fundamental equation that is basically the entropy should be expressed as bunch of extensive variables, and x naught is usually denoted by internal energy. And this is the fundamental equation expressed according to the so-called entropy scheme. Okay. So as I mentioned, but I didn't really show, is that actually this one is shown in the last lecture. Temperature is actually defined in this way. However, if you continue to use similar arguments, you'll find the formal definition of pressure is actually like this. And the chemical potential would be something like this. Okay. And here, this T is the temperature as we established. And also there's an important concept that this T is actually an intensive quantity. Okay. So it is what do we mean by intensity? It just means that if you have a system with temperature T, and if you scale your system up, maybe double the system size or triple system size, this temperature is actually not going to be changed, okay? But the particle number or energy will basically scale proportional to your system size. So that's what we call the extensive quantity, okay? So there's a general structure that's basically, for those intensive quantities, they are defined as the ratio of two extensive quantities, because those extensive quantities will scale with the system size in the same way. So when you take the derivative, there's basically the scaling of the system size will be cancelled. Okay. So similarly, the pressure P is an intensive quantity, and chemical potential is also an intensive quantity. Okay. So, so the idea is that using this expression of our entropy, basically we can express the temperature as a function of the internal energy, the volume, and the particle numbers. Okay. So once you have this relation, what you can do is that you can try to invert that and try to construct the energy or the internal energy as a function of the temperature and particle number and volume. Okay. So if you have that, then from this, the definition of the pressure, originally you will have pressure as a function of energy and particle number and volume. Now you can replace the energy using this expression, then you'll see your pressure can be expressed as the temperature, as a function of temperature and particle number and volume. So there are ways that you can change the variables accordingly and try to switch from one description using the extensive variables and try to express it using the conjugate intensive variables. Okay, so so here is just the general structure of that. So so this is the fundamental equation, and usually it is described by the entropy scheme, which means that we want to maximize the entropy to find the equilibrium configuration. But there's an equivalent statement. Is basically we try to describe the fundamental equation starting from using the entropy as our variables. And we want to change that to use the internal energy to describe our system. Okay. So to some extent, this is just a change of description, but doing this change of description actually got a name, because energy is also something that we are more familiar with, or we are more comfortable with. So this type of description is also called the energy scheme of the fundamental equation. Okay. So here I'll just write down the variational principle. It's basically we want to maximize. Okay. And we want to minimize. Okay. So so I think we usually heard this kind of statement. So I'll just try to give a very pictorial description about that. And there are some formal proof for this variational principle, which might be a useful exercise for you, but I'm not going to elaborate that here. So let me just try to explain what that means using the concaveness of our entropy function. So let me just try to write down a formal expression about the function of the function of entropy as a function of extensive variables. Okay, so what this graph means is that the vertical axis is just the entropy, and one of the coordinates special is the internal energy. Okay, and the rest of the extensive variables x1 to xr, I just pack it into one direction. Okay, because if I really draw many of them, it will be impossible to imagine what I'm talking about. So let's start by considering what do we mean by entropy is a concave function. So it's a bit difficult to draw. Let me try. Okay, so what do we mean by entropy is a concave function? It just means that the relation between entropy and other variables are basically some kind of function that has second derivative that is smaller than 0. Okay, so if we try to plot it in a higher dimensional space, it's basically some kind of surface that have this kind of shape. Okay, so let me extend these coordinates a little bit further. Okay, so at this particular point, I'll just label it as the equilibrium configuration of the of all the rest of the extensive variables. So let me try to draw it here. Okay. So when we are using the entropy scheme, basically what we are talking about is that we want to, if we give a specific energy, for example, let me call this E star. Okay. And let me draw, try to draw another surface which represent the plane with fixed E star, and basically this plane will cut the surface of the entropy function in a specific way, like that. Okay. So the first thing is that obviously we can see that this entropy is a monotonic increase function as a function of internal energy, so there's no problem. And for a specific given energy E star, the equilibrium configuration actually corresponds to the maximize the value of the entropy. That is basically this spot. Okay, let's call this spot the spot 1. So what do we mean by that is basically if we look at the spot 1, the change of entropy at this energy E star, if we leave a little bit away from the equilibrium configuration of the rest of the extensive variables, this change will be smaller than 0. Okay, because it is the maximized value. So it's like if you move from this maximum value to somewhere else, you will always the entropy will always get smaller. So that's the spot 1. that basically correspond to the variational principle for entropy that we want to find to maximize the value. So as I mentioned, because the entropy is basically a concave function, so it will be equivalent to saying that if we try to consider the case where we have a fixed entropy, then what we are doing is actually we are making a cut somehow horizontally. Oops. Okay. So if we are making this cut, then it is obvious that basically the maximize the entropy configuration, which correspond to this equilibrium point 1, is equivalent to that you are trying to using the energy as your using the energy scheme to describe the fundamental equation, then that corresponds to the variational principle that you are looking for minimize the energy, because the spot 1 using this green line or this green cut actually correspond to the minimum value of the energy. Okay, so that's a very pictorial way to understand that. So so basically that's the variational principle for the energy scheme description. So are there any questions so far? Okay. Yes. Why what are connected? Can you say that again? 你说哪两条线？绿色和那个什么蓝色吗？哦，因为那个是它一开始是一个曲面，然后我们做的事情是我们选了一个特定的能量叫 E star。那意思是什么？就是你有一个很大的一个大平面切下来，然后那个蓝色的线基本上就是你切一刀以后的那个边边这样。想象你有一个粘土，然后你直接把它切开这样。然后你有另外一种切法是你切横的，那就是绿色。对，有点像球的东西。对，你简单的想法是你可以把它想成球，但球下面会包起来，但这个不是球，因为它下面不会包起来，它基本上是，对吧？就一个凸的这样。应该说不一定要包起来啦，但它基本上是凸的。对。Okay, good. Yeah, so there are more formal algebraic way of proving that in the textbook, but I'll leave that for you to experience the argument. But the whole point is that if you use this geometric way to interpret what's going on, it's almost like trivial. You don't need to go through the algebra. Okay. And the purpose of this course is basically a very quick overview about what thermodynamics is. So if you are interested, I still encourage you to do the algebra approach. Okay. So now I'm going to talk about another very important concept in the thermodynamics that is basically the Legendre transformation. Okay. So Legendre transformation is so powerful or like so useful that you encounter in thermodynamics, and you also encounter it in classical mechanics. Okay, so one of the very important idea of the Legendre transformation is basically we are doing some kind of change of variable. Okay, so here I'm going to give you a very intuitive understanding what kind of variable we are using and why we are changing that. Okay, so basically the idea is that if we have a function we can of course describe it using the original variables. But we can ask ourselves, can I describe this function using the slope or using the tangent of this function? Okay, and it turns out that this is basically what Legendre transformation is doing. So let me try to write down the question more explicitly. Let's assume that we have some function that is described by two variables. One is x and the other is c. And as a physicist, we assume everything is smooth and we can take any kind of derivative we want to. So I'll just keep that as the nice property for this function f. And the question is, we want to express it. Okay, so the claim is that we want to express this function by the slope of f on the x direction with a fixed value of c. Okay, so of course you after some discussion you'll realize that this is probably some very problematic, but I'll show that why it is problematic. So the first question is it possible? So let's try to think about a procedure that this might be possible. So suppose we define P to be this quantity, which is partial f partial x at a fixed c. Okay. So eventually we'll just do some derivatives and we'll put c as it is. Then we'll have some function g, which is as a function of x and with parameters c. Okay. Then what we can do is that we can say, once we have this relation, we can invert it. Then we got an expression for the x coordinate x as some kind of function. Let's call it g tilde. Now with the parameters or the variables p and the parameter c. Okay, so that's like one route that we can do that. And why do we want to do that? The reason is simple, because we are trying to find the expression of this function in terms of its slope p and the c. And once we are able to replace the variable x with some parameter that's basically p and c, then we are done, right? So the next step, yes? Can you say that? Oh, it is blocked or okay? So let me try to get to somewhere that's safe. Okay, good. So the strategy is simple. We insert. Oops. Basically, we'll have something that looks like this. And we can define it as the new function phi, p c. Then it seems like we achieve our goal if we follow this strategy, right? So the fact is that we are almost there, but just not yet there. The reason is if we consider a function, okay. If we consider the function, say f1 as a function of x c, and another function f2 is also a function of f of x and c, but now it is related to the f1 function, but with the x coordinates adding a arbitrary function, basically psi of c. Okay, you can always construct such function. And what you will find is that if we follow these two procedures, procedure 1 and procedure 2, basically we got the same phi of p could c. Okay, you can try to show that afterwards, but I'll just tell you that you will get the same result. And so what that means is that this procedure that we just achieved using step 1 and step 2 did not really give us a unique answer. Okay, so that's a problem, because if we want to faithfully represent our original function, it had better give me the same result. Otherwise, there's some problem about this procedure. And the intuition why it happens is that suppose we start from some like two functions. One is called f2. This is f of x, and the coordinate is x. And the other is f1. Okay, and the f2 and f1 are related by a homogeneous shift. Okay, suppose we start from here, and if we ask what is the slope of this function, basically we'll find that df dx is basically the same value. Okay, because it's just a constant shift. When you take derivative, nothing changes. So so that means that you cannot use the slope of this function to inverse or to reverse construct your function f. However, if you add a little bit more information about your system, that is, suppose you have a function f that looks like that, and instead of just the slope, you want to construct the tangent at every point of your curve. For example, the tangent might look like this. The last one is badly drawn, but okay. Then you are able to uniquely determine what is the original curve. And the reason is because now, in addition to the slope of your tangent, you also specify what is the intersection of this tangent with your coordinate system. Okay, so it is possible to do that. So let's try to see if it is this case how we construct the the tangent of our system. So let's see. So this is x equal to 0. Let me just take this point as a reference. So this is f of x, and here's x. Okay, and let me assume that this intersection at x equal to 0 to be y for this particular tangent line. Okay, so how to get the equation for this straight line actually is that you can just simply write it down according to some high school math. This is basically a definition of the slope for this tangent, right? Because the difference of x is just f of x subtract y, and the difference in x is x minus 0. Okay, so from here you can uniquely construct that y is basically f of x subtract x times partial f partial x. Okay, so this is for this simple single variable expression. So the only difference is that you need to add this additional term. So similarly, if you take this idea and try to use that to improve our previous step 1 and step 2, basically we already almost get the results, but the correction that we should put in is that in addition to express your function using this inverted relation, you need to subtract this is just like the x in this expression. Oops. And then this slope is basically the p in our definition. Okay. So that's basically the spirit of Legendre transformation, and you can try to convince yourself like how to generalize it into multivariable system. But basically, that's the idea. You express your function using the tangent of it. Okay. So now, why I'm going to talk about that, because the next subject I'm going to talk about is the thermodynamics potential. Okay, so are there questions so far? Okay, if not, I'll continue. So basically, the idea is that when we discuss the thermodynamic potentials, we realize that we want to use some concept that is similar to potential, but to describe our system using the intensive variables. For example, the temperature, the pressure, and the chemical potential. Okay, so so how to do that? At this moment, we only know that the fundamental equation of our system is described by the function entropy and a bunch of extensive variables. Or if we use the energy scheme, we have the function energy described by a bunch of extensive variables. So the next step is that we just learned what is the meaning of Legendre transformation. Maybe we can use that, use basically the Legendre transformation to convert our expression of the fundamental equation into the thermodynamic potential that is described by the intensive variables, which is the differentiation of the entropy with respect to some extensive variables. For example, for the temperature, it's the entropy taking the relative with respect to energy and invert that. So, okay, so I think I'll stop here, and I think I elaborate what's the logic behind it. I think we'll continue the discussion of thermodynamics principle in the next lecture, and we'll take a 20-minute break and see you afterwards. Okay, so I think we'll start our lecture. So one thing is that I have a typo somewhere here. When we discuss this heat engine, the temperature should be entropy taking differentiation with respect to energy, but take an inverse of that. That's the temperature definition. So it should not affect any of the derivation, because I think I got it right in the later part. So that's one thing. And the second thing is about this picture that here we are making a very general description about what is the function of entropy. So at this point, you might feel like it is not very clear what that is, because usually when we say there's a function, what we imagine is that we have a function as several variables, and there are coefficients, and we add them together, and maybe they are exponential of something, things like that. But here I'm trying to take the approach that we try to be as general as possible and try to only limit the behavior of this entropy function by asking it needs to be concave. Okay, so that's the approach we are taking. So what that means is that if you try to use this formalism to describe a system, for example, like ideal gas system, you might have a functional expression that have a bunch of parameters inside. That entropy function might have details. Maybe the shape is a little bit different with another system, maybe, for example, a solid state system, and you can still construct this entropy as a function of extensive variables. So the shape might not be the same, but the key point is that they are concave. Okay, so that's the one thing. And the other thing is that there's a very good question basically asking, if I try to accept this picture that the entropy is a concave function, then the maximized entropy principle is almost it is almost trivial, saying that it is equivalent to the minimized energy scheme. Okay, so isn't it just some kind of cheating because we kind of put that in by hand at the very beginning instead of saying something physical? So actually, the answer is yes. The whole framework that I try to formulate right now is trying to postulate what entropy function looks like. And the reason we make this postulation is because we want to find the easy way to encapsulate the relation or the information in the thermodynamic theory. Okay, so to some extent, no matter what we did, this assumption had better create consistent results with our understanding of thermodynamics. So in that sense, we put in the answer by design. Okay, so that's one thing. But there are two ways to think about that. The other way to think about that is sometimes in the study of science, we start from some well-established system, and we get some kind of conclusion. And we found that maybe we can use those conclusions as the new principle or the new fundamental as our starting point. Okay, so if we take that idea, maybe the postulate that we made that entropy needs to be a concave function actually can be to some extent another type of fundamentals, but that is a challenge or a question mark statement. It will depend on your taste, but at least if you are very conservative, the simplest way to think about this formalism about why we make this assumption about the entropy is because we want to find an easy way to encapsulate what we have learned in thermodynamics previously. Okay, and this approach actually, to some extent, there's no much physical content inside, but it's just a very efficient way to let us understand what is the framework and the structure for the thermodynamics. Okay, so then the question is, why do I want to take this approach? Because once we know, entropy function plays a key role in understanding the whole framework of the thermodynamics. When we enter the description of statistical mechanics, we can ask, when we try to understand statistical mechanics, can we construct the entropy in the sense that it satisfies all the criteria that we discussed here? Because if we are able to do that, that means that statistical mechanics can really serve as a microscopic theory to understand thermodynamics. So that's like basically why I'm taking this approach. Okay, so let's continue. And also, I think the topic that we are trying to discuss is that we want to develop some kind of idea. Basically, is the thermodynamic potential. So the purpose is that, okay, so basically is we want to identify the state of equilibrium that exhibit a given value of intensive variables. Because usually what we can, or usually what is more physically meaningful is the intensive variables. Because, the property of energy or the absolute value of the energy, of course, will scale for bigger system. So we are trying to reduce that effect. So, okay. So how to do that? Like, how do we assign a specific intensive variable to our system? Is usually that we consider our system to have some contact with something that is like a heat bath that's big, but it has some intensive variables that is kept as fixed. For example, the definition of heat bath is that the temperature is fixed. Okay, and the system can, of course, exchange energy with our heat bath. But of course, you can change the property of your heat bath by saying that, oh, the heat bath is used to fix the specific value of the pressure. That's also possible. Okay. So as we already discussed, that the Legendre transformation basically try to help us to describe the function according to its tangents. Okay, and the tangents contains the information of differentiations. So if we try to discuss a system with a fixed temperature, one of the very useful thermodynamic potential is called the Helmholtz free energy. Okay, usually we denote it as f of t and x, and here x stands for the rest of the extensive variables. So now you can take a look about the expression of that. Basically, it will look like this. So so now you see that what Helmholtz free energies means. So basically, you start from some expression of your energy of your system. Okay, the energy of your system, of course, will be a function of entropy and the rest of the extensive variables. Okay, but in order to study a system with the fixed temperature, what you are trying to do is that you want to convert the variables from the entropy as a function of the rest of the extensive variables. You want to convert that into expression of entropy as a function of the temperature. Okay, so according to the Legendre transformation that we just learned, basically what we need to do is to include the corresponding slope-like object in this case. So in this case, the function that we are expressing is the energy. The slope-like object will be this object, which is the temperature that we are familiar with. Okay, and this entropy as a function of Tx to some extent is the G tilde of Px that we just derived in the Legendre transformation formula. Okay, so you can see that if we try to use that to understand what is the meaning of Helmholtz free energy, it basically is that we want to describe energy, but instead of using its original variable, we want to describe with its tangent. Okay, so I think I forgot to mention that, but let me just try to write it down. Okay. So energy at first is described by entropy and other extensive variables. So we are trying to change that. And it will be a free energy as a function of temperature and other extensive variables. Okay. So in this case, we can still ask what is the variational principle once we make this change of variables, and it turns out that we are still trying to minimize the free energy for equilibrium state. And this is a very peculiar one where we convert the description of entropy into the description of temperature. And it is widely used because most of the experiments we use temperature as a control parameter. So it is very useful. Okay, but from a formal perspective, actually, we are free to change any kind of extensive variables into its intensive conjugate partners. So this similar idea will be conveyed using this generalized version of the thermodynamic potential. Let's use it phi to denote it. So maybe if we want to describe any of the if we want to replace the description of our extensive variable x1 by its conjugate pairs f1, then the corresponding thermodynamic potential will look like this. And here this f1 is defined as the partial differentiation of energy with respect to the extensive variable x1, where x1 is inverted accordingly. So the example of such a generalization includes the Gibbs free energy, where usually is denoted by G, and the extensive variable is basically the pressure P. The rest are the extensive variables, and also enthalpy. In this case, we keep the entropy and we replace the volume by its intensive conjugate partner pressure, and the rest of the extensive variables are kept. Okay, so that's the very basic idea. So in addition to such ideas, basically we can try to think about what we have achieved till now. So we found that this assumption about the entropy as a function of extensive variables to be concave is useful. It tells us a lot of the property, and also it tells us how the system reaches equilibrium according to the assumption that entropy should be maximized. Okay, so but something that is kind of hidden in this concave assumption is about the stability of the system. Okay, so I'll leave it as an exercise to think about. So the first thing is that at equilibrium, we have temperature. Suppose we have two systems, right? System 1 and 2, and the wall now is very, free to exchange the energy, or like it can be moved, so the volume can be changed, and now particle can penetrate between these two chambers. Okay, then the equilibrium condition we can derive by maximize the entropy function. So T1 equals to T2, and correspondingly the pressure 1 must be equal to pressure 2 in order for this wall to be fixed at the middle, and the chemical potential 1 should be equal to chemical potential 2 in order for these particles to carry the same amount of free energy. Okay. So also in this very quick review, we show what T is, and basically energy flows from high T to low T. Okay, and we also show entropy is concave, and it is equivalent to saying that energy is convex in the corresponding parameters. So the third thing is about the stability. The stability is basically an issue that we did not really discuss till now. The idea is that some quantity must be we have some restriction about that in order to have a stable phase. So here the restriction that I'm going to discuss about is the heat capacity. According to the fundamental thermodynamics, we know it is defined in this way, and the heat capacity of the specific heat, it must be greater than 0. Okay, in order for this system to be thermodynamically stable. Okay, so the first question is why it is so. So to some extent, C is greater than or equal to 0 is related to some extent, it's like the change of the heat of your system as a function of the temperature should be greater than 0. Okay, so what that means is that for your system, the change of heat and the change of the temperature should have the same sign. Okay. Okay. So what that means is that suppose you have a system and maybe you have a subsystem. Okay. And usually when we say that we have a system with temperature T, what that means is that more or less it is with temperature T, because as we discussed in the first chapter or last few lecture, we know that physical observables, usually there are some small fluctuations, but because of the system size is so large, so this small fluctuation is basically tiny compared with the mean value, which is the macroscopic observable. So one of the questions is, will those small fluctuations basically break our system? Okay, so if the system is a thermodynamically stable system, this small fluctuation should not kill our system. Otherwise, the whole description doesn't make sense. So let's try to assume that we have our system, and we have the system with temperature T, and we try to choose a subregion, and suppose this subregion is of temperature T1. Okay, what that means is that because of the fluctuation, some part of the particle might vibrate more, and some part of the particle might vibrate a little bit less. Okay, so in this region, the particle just vibrate less compared with its neighbors. So we kind of assume that if T1 is smaller than T, what will happen? Okay, so that's the question we are trying to ask. So if C is greater than 0, let's assume C is greater than 0 or equal to 0, then we can ask what happened to this region, because now T1 is smaller than T. So what that means is that the energy will transfer from its neighbor into this small system, right? So once energy gets into this small system, what it is going to do is that because C is greater than or equal to T, so that means that the energy of this part will basically increase. So since dq is greater than 0, and we ask dq dt is greater than 0, that implies dt is greater than 0. Okay, so what that means is that for this small region, even though at first the temperature T1 is smaller than T, what the system is trying to do is that you will input more energy into this small region and the temperature grows back. Okay, so that's a good thing because it tries to recover the temperature difference with its environment. So nothing is bad is going to happen. But you can ask what happens if C is smaller than 0. Okay, when C is smaller than 0, what is going to happen is that there's a region called T1, and as we know, temperature flows from higher temperature to lower temperature, so dq enters. Here dq is greater than 0, but because C is smaller than 0, what it tells us is that dt will actually be smaller than 0. Okay, so that's bad because it just means that when energy flows into this low temperature region, actually this low temperature region gets temperature that's even lower. So that's really bad because it means that the temperature fluctuation now is going to be larger and larger, and eventually your thermodynamic description is not going to be a valid description. Okay, so in that sense, usually whenever you have some strange system, and you calculate the specific heat of that system. And if it is smaller than 0, usually what we call is that this system is thermodynamically unstable. Okay, just because the temperature fluctuation actually is not going to be suppressed. Instead, once you have some lower temperature region, that region will become some kind of cancer that you will just suck up all the energy, and the temperature actually will get lower and lower, and the situation of the temperature distribution is not will get more and more rough, and the difference will become larger and larger. Okay, so that's one of the criteria for the system to be thermodynamically stable. The other important criteria that you usually will see is something called kappa T. It's called the compressibility, and it is defined in this way. And it is also required to be greater or equal to 0. Okay, so similar arguments will apply to this this quantity, because what this quantity is telling us is that if the pressure changes, or if the volume of the system changes, how the pressure change. Okay, so this is basically what this relation is telling us. So we can make similar arguments. Suppose we have a big system with some background pressure P, and this subsystem, let's assume that it has some pressure P1. Okay, so according to our intuition, we know that if suppose P1 is smaller than P2, what is going to happen is that the system will apply some force to this small region. Okay, and then the volume of that region 1 will be smaller. Okay, so dV will be smaller. Okay, so if kappa T is greater than 0, it means that partial V, partial P needs to be, let me think. It's greater than 0, and this is greater than 0. This thing needs to be smaller than 0. Okay. So if this thing is smaller than 0, then everything is good, because if dV is smaller than 0, that means dP is greater than 0. Okay. So in this case, when I compress this small region, it will respond such that by increasing its pressure. So again, you will its feedback is good, because it tries to get back to the pressure of its neighbors. Okay. However, if kappa T is smaller than 0, then basically we'll get an opposite result, that when the pressure is trying to compress this subregion, what's going to happen is that the pressure change will actually be smaller than 0, which means that this region will actually have a smaller pressure, so the system will compress this smaller region even stronger. Okay, so that means that the fluctuation of your pressure now will also be increased if it is the case that kappa T is smaller than 0. So that also means that this system is mechanically unstable. When it is mechanically unstable, that means that basically, the system will crash, because if you have a system at the very beginning, it just fluctuates in various different ways, and there must be some small region that has a smaller pressure, and then with the smaller pressure, if this mechanism holds, then this small pressure region will be compressed even further, and the whole structure of your system will basically be broken. Okay, so that's why it is called mechanically unstable. Okay, so I think now we have went through a very quick overview about what is thermodynamics, and try to encapsulate everything we think is stating about the properties of entropy. And of course, I leave a lot of the holes in our discussion that I didn't went through, and I will leave it as an exercise or as an review for you to reflect yourself about what you have learned in thermodynamics. Okay, so in the next lecture, we will start or enter in the real core of statistical mechanics by thinking about the statistical postulates. As we mentioned in the very beginning, using the ideal gas example, we just assume the statistical independence of the velocity and position and all that, then we get really nice results that's compatible with our ideal gas model. But now we want to ask, if we want to take this approach from a more general perspective for different systems, how to do that, okay? So the key idea that we are going to do, or we are going to discuss, is about to build a relation, basically postulate by Boltzmann. And this omega is basically the phase space volume. Okay. So as I already mentioned, in order to understand that, we need to understand what is phase space and why we want to start with phase space. What's the important property such that connecting our understanding of entropy from phase space is a reasonable assumption. And starting from there, we'll try to construct a theory, or at least some idea of the theory of probability. That's called the ensemble theory. And there we will discuss something called canonical ensemble, and microcanonical ensemble, and grand canonical ensemble. Okay. Then once we know this, the meaning of these ensembles, we'll need to introduce the idea of partition function. Okay. So the reason that in the first homework you did a lot of normalization calculation for different probability function is because the correct way to interpret partition function is that it is basically a normalization factor for different ensembles. Okay, so once you understand that, you will realize that the structure of the theory actually provides you a good connection using this normalization constant to the thermodynamic potential that we are familiar with. Then starting from there, we are able to calculate the expectation values of different thermodynamic observables. And we'll need to discuss how these observables are related to the microscopic physics that we are interested in. Okay, so that's basically the rough idea. So I think we'll end our course a bit earlier. So I think the rest of the time, I'll encourage you to dig out your thermodynamic course lecture notes. I'm not sure when you took that, but you can try to refresh your memory about what thermodynamics looks like. And if you think it is just too much, like, you know, it's a whole lecture of the semester, I would suggest you to read the textbook, basically the chapter 2 of politics textbook. And the lecture I gave basically is based on that. So I just, in today's lecture, I just tell you what is the logical structure of that, but you can fill out the flash of this structure by reading the chapter 2 of politics textbook. Okay. So that will leave you as a reading material, and we'll end our course today here. And in the next lecture, we'll start from the statistical mechanics. Okay, and see you next